So, in the last lecture we have seen what are the different actors like a statistician, a probabilistic engineer or probability engineer, then a reliability engineer and a marine engineer, who all jointly play a role to estimate the reliability or formulation of reliability problem in a given space. Now, let us quickly see there are two important methods by which reliability studies can be carried out easily for a linear limit state function, for a nonlinear limit state function, which we call as FOSM and AFOSM. FOSM stands for first order second moment method. AFOSM stands for advanced first order second moment method. Now, in first order second moment method, first order of Taylor series expansion or I should say Taylor series approximation, not expansion, of the limit state function is used. That is why it is called first order. So, you approximately formulate the limit state function using Taylor series, and in that series you consider only the first order terms, okay. And if you do that, then that method of reliability is generally called as FOSM method. Further, only the second moments of the random variables are used to estimate the probability of failure. Let us say the limit state function is defined as m is equal to r minus s. M is the margin of safety, where r and s are statistically independent. They are also assumed to be normally distributed. So, one can say mu m and sigma m as mu r minus mu s and sigma r square plus sigma s. I call this as equation . Therefore, probability of failure is m less than 0, that is r is lesser than s, what is the probability of m less than 0? Which can otherwise say probability of r minus s less than 0. If m is a normal variate, because r and s are normally distributed, then we already know this probability of failure is simply given by phi of minus mu m by mu r, sorry, sigma m. Equation number, where the reliability index beta is nothing but mu m by sigma, and phi in this case is the cumulative distribution function of the standard normal variate. Okay. I can substitute for mu and sigma m as we saw from the equation number 2. So, probability of failure can be 1 minus phi of mu r minus mu s by sigma r square sigma s. Phi of any function can be 1 minus phi of this. This is of course the root. The equation number, let's see, I call this as 4, this as 5. If r and s are log normal, we have already given you this equation. You can easily tell me what is the probability of failure. We have already given you this. It is 1 minus phi of when they are log normal distributed, natural logarithm of mu r by mu s one plus v r v s square. This is v s and v r. This is equation number 6. If they are log normal, we have this equation. If this normal distributed, we have this equation. Now, FOSM method has some advantages and disadvantages. The advantages are the following. It is easy to use because you should know only the mean and standard deviation variance of R and S. Okay, you can find the probability of failure directly using these two expressions of 5 and 6 if they are normally distributed or log normal. So it is easy to use. Most importantly, it does not require knowledge of distribution of random variables. Disadvantages are results can cause serious error if the tails of the distribution function cannot be approximated by normal distribution. The second disadvantage could be value of reliability index depends on specific form of limit state function. As in this case you have seen that you are considering only first order approximation of Taylor series expansion. So it depends upon specific form. That is very very important why advanced FOSM was introduced. Okay. The value of reliability index depends only on the specific form of limit state function, that is very important, it is form dependent. This is what we call as an invariance problem. Let us talk about advanced FOSM. We all understand that it is necessary that all mechanically equivalent limit state functions should give same beta reliability index. On the other hand, it should not depend on the form of the limit state function. Now we all know that beta provides reliability index only if the random variables are not statistically dependent. that is if they are independent then beta gives the reliability value, and they should be normally distributed. That is why we said calculating reliability index using FOSM does not require any knowledge of distribution of random variable. It is understood that the random variables are normally distributed. If these two conditions are violated, then how to estimate reliability function or the reliability index beta, that is the question. So, that is addressed in advanced FOSM. Hasofer-Lind has given a method or a algorithm based on which the reliability index can be computed. Hasofer-Lind method is an advanced FOSM method which we will discuss. There are some limitations to this method also, we will also discuss them. Now, the key point in this method is it estimates a design point which is at minimum distance of failure function from the origin. I will come to that. Let us say I have two variables x2 and x1. I have a linear failure function, that is a linear failure function. To this linear failure function, I must find a point on this failure function, so that that point remains at a minimum distance from my origin. So, obviously, I have to draw a perpendicular and this becomes my point and this becomes my minimum distance. I call this as a design point. Okay. Now, if the function is linear, you can easily find this. If the function is nonlinear, for example, then if I take a point here and draw a tangent and say this is my minimum point, if you take a tangent here, you will say this is my minimum point. So, beta keeps on varying, is that clear? So, if the function is linear or non-linear between variables x1 and x2, how to handle this? So, the whole key issue in Hasofer-Lind method is to estimate a design point which is located on the failure envelope or the function which is minimum distance from the origin. Okay. Now, one may ask why it should be a minimum distance, why not maximum? Okay, I will answer this question. Hasofer-Lind method says the minimum distance is the safety index directly in its geometric meaning. So, the minimum distance, if it is estimated geometrically, that itself is the safety index. or beta. To be very specific, we write beta HL. HL stands for Hasofer-Lind. Now the method is very simple. The method actually transforms the random variables into a reduced form. I will come to that, what is a reduced form. The reduced form of random variable is defined as x dash ith value which can be xi minus x bar I by sigma xi for I equals, let me call C equation number, what is the number? 7. So instead of using directly the random variables which are R and S, I am going to use a modified or reduced form of the random variable x dash, where x dash will be value given by this expression 7. Now the interesting part is this reduced form or this reduced variable will have a 0 mean and unit or unity standard deviation. Okay. Now the performance function g of x 0 is now converted into g of x dash equals 0. I am not transforming the variables from x to x dash. Reliability index, which is beta HL, which is the minimum distance of the performance function from the origin, is given by where x dash d is the minimum distance of the design point from the origin. So, D stands for the design point. Some literature refers this also as checkpoint. So, design point or checkpoint. Now, let us say two cases. Case 1, when the limit state function is linear. When the limit state function is linear, we will see how to handle this. So, let us consider m as r minus s, which is equal to 0. The reduced values are r dash and s dash, which are r minus mu r by sigma r, which is s minus mu s by sigma s, equation 10. So, I must substitute r and s here. I have r and s here. Rearrange these terms. I can rewrite m. Now, substituting 10 in 9, m can be rewritten as sigma r r dash plus mu r minus sigma s s dash plus mu s. Call equation number 11. So, my limit state function will look like this, which can be r dash and s dash. It is a straight line, okay, it is a straight line r minus s. This will limit state m is equal to 0. And this is my beta HL, and this becomes my checkpoint, and this is my failure state where m less than 0, and this is my safe state where m greater than 0. You can see here for all values here, for all values, for example this point, you can see the slope is gentle, is when r is greater than s, okay, safe state, whereas in this case it is going to be failure state. Now, you can see from this figure, as the limit state function moves closer to the origin, what will happen when this line keeps on moving closer to the origin? The failure state will be keep on increasing, okay. The failure state, or I should say the failure region, keeps on increasing. So, there is a level at which their failure state is optimized, and that is controlled by the minimum distance from the origin, okay. Hence, beta can be seen as safety index okay. That is the reason why the minimum distance is considered as reliability index in Hasofer-Lind technique, okay. Is this clear? Now let us move to the so in my case beta HL can be simply mu r minus mu s by sigma r square sigma s square. What is the equation number? 12. You will see that this expression is same even in the case of normal variates, isn't it? The expression is same. The above expression is similar to that of reliability index of normal variates, random variables, isn't it? That is why beta HL is also called safety index or accepted reliability index. Remember, beta HL equation has been derived using the geometric calculation from this figure, it is not from the formula, okay. It is a very simple issue that I want to find the minimum distance between the line from the origin, 2D geometry problem, okay. Can easily find this. I have not shown the mathematical working out of finding out beta HL geometrically, I will get this equation, but this equation is fortunately same as that you have for the normal variates. Therefore, I can call this minimum distance as reliability index. That is the definition why Hasofer-Lind index is called as a safety index. Now when the limit state function is nonlinear, now it is linear, so straight line, okay. When it is nonlinear, what happens? In this case, computing a minimum distance becomes an optimization problem. So what you have got to do is beta HL is nothing but the distance which is given by x dash transpose x dash we have got to minimize this. Subject to the condition g of x dash is set to 0. For many random variables x1 x2 xn which originates from the safe state g of x dash less than 0 indicates failure. Therefore, g of x dash greater than 0 denotes the minimum distance from the origin to a point on the limit state function which is called design point. So, the problem is reduced to determining the coordinates of D design point geometrical or analytic. So, by this definition, reliability index becomes invariant. Because regardless of the form of the limit state function, the geometric shape and the minimum distance remains constant. The one which was a difficulty in FOSM is now handled by Hasofer-Lind by a different technique, because now by obtaining the coordinates of this point D for any form of the geometric shape of the limit state function, the minimum distance will remain constant, has to remain constant. Let us say the plot of these two variables x2 dash and x1 dash for a nonlinear limit state function looks like this. Let us say this is my design point. I call this point as x dash. So, this is my design point, and this is where g of x dash less than 0, and this is the distance what I call as beta HL, and this is the function g of x dash equals 0, and this is a function, this is the area where g of x dash is greater than 0. So, this is Hasofer-Lind reliability index for nonlinear limit state function. So, from this figure one can see that x dash is the design point, also called as MPP, most probable point. So, minimizing d, which is equal to square root of x dash and x, subject to the condition g of x, that is g of x dash, should is equal to 0, because I am transforming the coordinates from x to x dash. That is what we are doing in advanced methods. Using Lagrange's multipliers, we can find the minimum distance beta HL as minus of sum of I is equal to n x dash di, d stands for the design point, I is the summation, is what equation number is this? 13. Where dou g by dou x dash di is the partial derivative why it is partial derivative? The values of x are no more independent, okay, evaluated at design point d with coordinates x dash d1, x dash d2 and so on. These are the coordinates of the design point. So, this study has got a very interesting reference. I wanted to give you the reference, Shinozuka M. (1983). Basic analysis of structural safety, Journal of Structures Division AC, (1093), 721 to 740. The design point x t dash I, because I am interested only in finding the design point, is simply given by minus alpha di beta h. Is equation number 14. Where alpha di can be dou g by dou x di dash divided by root of summation of 1 to n dou g by dou x dash di square. Equation number 15. Which are direction cosines along the coordinate axis xi. So, in the space of original variable, because x dash are all reduced form of variables, in the space of original variables the design point can be given by x dash di is mu xi minus alpha di sigma xi beta h. That is equation 16. Of course, this method has got few limitations and there are improvements suggested on this method which we are not discussing in the scope of this lecture. So, in this class, in this lecture, we have seen two interesting cases where I have picked up the first order second moment method of reliability analysis and showed you how to find out the safety index or reliability index for a given standard variate which is normally distributed, but we have seen that limitation for FOSM is that it depends upon the form of the limit state function. If it is linear, it is giving different answer, if it is non-linear, different answer, but strictly speaking it should not. Then advanced method have been suggested by Hasofer-Lind, saying that generalize this function in a different reduced form which has got unit standard deviation and zero mean process, and find out the coordinates of the so called design point or the check point or maximum probable point on the limit surface. So, this becomes an optimization problem. You have got to minimize the distance d with respect to the failure function as we have discussed in the case. So, as the process goes ahead, we can easily find the design point coordinate using this expression where beta HL will give me. So, this process is a iterative process. Okay. Initially you have got to assume that the reduced form of variables are all standard variables as mean and standard deviation. Find out from equation (15) or in our case equation 14 the new BHL or beta HL or you will find the x dash di in terms of beta HL. Then substitute back in the original equation of beta HL to find out the value of beta HL, substitute again back in equation 14, keep on getting new x di's. Okay. So, you will ultimately get the coordinates of the design point which does not vary between the first approximation of the standard variates to the actual real random variables which are dependent on each other. So, the corresponding BHL will give you the safety index of the problem. So, there are good illustrations and examples available in the literature. Unfortunately, in this lecture I am not able to show you some examples of the workout problems. If time permits, we will see as an appendix later in the end of this course, but still as a part of this particular module we are only introducing reliability in the scheme of advanced marine structures. We have discussed that in length. So, I wish that you have understood the fundamental concepts of reliability as applied to marine structures. What are the limitations, what are the different levels, what are uncertainties, where are they formed and how are they responsible, how are they interdependent, how do they control the whole design process, why reliability cannot be accurate, how reliability can be a design scheme, what are the limitations, what are the fields of applications, what are the players involved in reliability methodology, and what is AFOSM and FOSM. That is the focus of this whole module which we discussed, and if you have any questions you can always address me to NPTEL IIT Madras under this scheme. I hope you will go through these lectures once again and try to understand. Of course, there is an advanced course on reliability, especially handle and marine structures, which will come up in the next scheme of NPTEL. You can look for that course where we will address only reliability problems and marine structures with classified site examples. Okay. So, we have finished 3 modules now. We have got one more module which will take up in the next class onwards, which will going to address the fatigue strength of marine structure members. Thank you very much.